All right, the next section in the Klein textbook is all about carboxylic acids and their derivatives. To start off, let's go over basic nomenclature for carboxylic acids. And the nomenclature is pretty straightforward. Let's take an example molecule that looks like this. And I'm going to have a carboxylic acid coming off the right-hand side. First thing you always want to do when naming organic compounds is to identify the longest backbone. So we've got a 6-carbon backbone here, which means that the parent is going to have the prefix hex, indicating 6 carbons. Specifically, we want to add the hex-an to indicate that it's an alkane group coming off of it, but the suffix does need to change to indicate that we've got a carboxylic acid. So in this case, what we need to do is we need to change the suffix to an oic acid to indicate that we're talking about a carboxylic acid and not any other functional group. All right, I did want to go over some other IUPAC functional names, or other IUPAC accepted names, I should say. And these, for the most part, are holdovers from pre-IUPAC times, but let's take a look at them. The first one is essentially half aldehyde, half carboxylic acid. Carboxylic acids take higher priority than aldehydes in naming, and this is generally just called formic acid. A lot of insects produce formic acid as a defense mechanism. In fact, if you've ever squished a bug like an ant, you may actually smell that pungent formic acid smell. The next one is pretty similar. Most of you have this in your kitchen. This is one of the simplest carboxylic acids. Some people are tempted to call this ethanoic acid, but that just sounds kind of funny. Most people just refer to this as acetic acid. This is really the concentrated form of vinegar. The vinegar that you have at home is usually about 5% acetic acid, 95% water. All right, we can keep on going. The next one is propionic acid. People don't call it propanoic acid usually because it just kind of sounds funny. This is one that smells really bad. It smells awful. Somebody once described it like the worst BO on the planet. The next one, and BO is body odor, excuse me. And then the next one we'll look at has one extra carbon. This is butyric acid. Butyric acid again smells really bad. It smells like rotten butter. So it smells like rotting dairy products. So imagine if you left milk out in your fridge for months or milk out on your counter for months at a time. That's what that would smell like. All right. There's a few more. One we've seen previously. This is called benzoic acid, where it's attached to an aromatic ring. Let me keep this black. And benzoic acid is pretty common. In fact, we made that in one of our lab videos. The next version just has a cyclohexane, and this is called cyclohexane carboxylic acid. And it's another precursor that's found in organic chemistry. All right, so it is important to remember that when you do number your carboxylic acids, the number 1 always needs to be the position where the CO double bond is. Regardless of where the other functional groups are, that's where your number 1 position needs to be. All right. So let's take a look at some of the diacids. So what happens if we have 2 carboxylic functional groups? And there's a wide variety of diacids that will show up both in organic chemistry and biochemistry. So let's go over them. The simplest diacid is when you have 2 carboxylic acids linked together, and this is called oxalic acid. The next one has 1 additional carbon in between. So it's got a 3-carbon backbone. This is called malonic acid. Next one, as you can imagine, has one more carbon in the backbone. This is called succinic acid. And then we can keep on going down the list. We'll add one more carbon. This is called glutaric acid. If you have 6 carbons, this is a compound we actually made earlier this year in lab when we ring open cyclohexane. This is called adipic acid. And then if you have one more carbon, meaning 7 carbons, you get a diacid that looks like this. And this is pimelic acid. I always had a really hard time remembering the names of all of these since they don't follow any of the IUPAC rules, but I'll show you the trick or mnemonic that I used when I was in school, and that was take the first letter of each of these, so O, M, S, G, A, P, and then remember it by saying, oh my, such good apple pie. I know it's cheesy, but the cheesier the mnemonic, the easier it is to remember. So this follows the first letter for each of these diacids. So I know it's kind of a goofy thing, but it got me through grad school. It can get you through this class. All right, so let's take a look at structures and properties. Just really briefly. Carboxylic acids are pretty unique in that they are quite acidic relative to other organic functional groups, and they really like to hydrogen bond with other things. So for example, let's imagine that we've got these 2 carboxylic acids. They'll hydrogen bond to each other and form a dimer. So really strong H bonding is one common property. Typically, the pKa for these carboxylic acids is around 5, but really the identity or the true value of the pKa depends a lot on the R group. If you have an electron withdrawn R group, it's going to make it more acidic because you're going to have some inductive forces pulling on that sigma bond as well. So the pKa is typically about 5, but occasionally it can go down all the way to about 0. Additionally, because of all this H bonding, they tend to have high boiling points. Typically, if you've got more intermolecular forces like this, where hydrogen bonding is occurring between multiple molecules, it's going to take more energy to rip them apart and get them into the gas phase. So that's just kind of our generic overview of the structure and properties of carboxylic acids. But now what I want to do is I want to go into the preparation of carboxylic acids really quick. And most of this is just going to be review from previous chapters. We'll cover a couple new reactions though. So let's take a look at the review ones though. And a lot of these we saw last term. So for example, if you have a primary alcohol, you can oxidize that primary alcohol to a carboxylic acid really easily, but you need a strong oxidizing agent. In this case, the best strong oxidizing agent we have is Na2Cr2O7, that's sodium dichromate, using sulfuric acid and water. If you remember, if we used PCC rather than this reagent, we would stop at the aldehyde, but in this case we purposely want to oxidize all the way to the carboxylic acid, so we're going to use the stronger oxidant. All right? The next reaction uses similar reagents. So if you remember at the end of last term, we said if you have a benzylic carbon like this with protons, that you can actually oxidize any benzylic carbon, even if it's an ethyl or isopropyl group, into a carboxylic acid as well. And we can go ahead and draw this out really quick. And you could use the chromic acid reagents shown above. Those also work down here. However, the commonly used reagents to avoid the chromium waste is going to be KMNO4, NaOH, sodium hydroxide, and potassium permanganate, water, and heat, followed by an acidic workup. So let's make a note that chromic acid also works. More and more chemists are trying to get away from these chromium-6 based compounds, so if you can use potassium permanganate, it's usually preferred. All right, so that's another method. We also saw that we can make carboxylic acids from alkynes. This was earlier on last term, and we said specifically if you do this, you're going to make 2 equivalents of a carboxylic acid, and that is because we're essentially going to be cleaving this triple bond in half, right? And to do this, all you need is ozone and water. It'll clip it apart. And it is important to remember that you'll generate 2 equivalents. If you have a proton here, meaning a hydrogen in this spot, the second part that you'll get would be CO2. However, if you've got an internal alkyne, you'll actually get 2 different carboxylic acids. All right, so that's an important one to remember for review. Let's take a look at one more. This one we'll be able to cover in more detail a little later, but for this one you can have a nitrile where you have a carbon-nitrogen triple bond. Sorry, this should be a clear nitrogen. And you can hydrolyze it. Just like we saw hydrolysis in our chapters with ketones and aldehydes, you can hydrolyze this using acid and water and heat, and we can get this to go all the way to a carboxylic acid. We'll come back and look at that mechanism a little later, but it's so similar to the hydrolysis that we've seen before. I'm going to throw this into our review section right now. All right, the last one I wanted to show you is how we can convert an aldehyde to a carboxylic acid. And we actually saw this rather recently in our aldehyde and ketone chapter. And this was our Baeyer-Villiger oxidation. And we can do this using, we can use a peroxy acid in order to accomplish this. And if you remember, this hydrogen migrates more readily than the secondary carbon, so the oxygen's more likely to insert in that position, giving us a carboxylic acid every time if you start from an aldehyde. All right, so I'll show you the newer method. The newer method is pretty cool. And it's kind of a variation of what we've seen previously. So I'll show you this really quick as an overview, and then we'll jump into the mechanism. And the idea behind this is, what if we have a Grignard reagent? Well, all you would need if you have a Grignard reagent to accomplish this transformation is CO2, meaning dry ice, even from a grocery store, followed by an acidic workup. And by doing that, you're going to install a new carbon from the CO2, and the CO2 is going to incorporate itself in, and then in that last step, when you protonate it, you're going to add that proton coming off the very end. All right, so let's take a look at the mechanism for this. All right, the mechanism's really straightforward. So let's say we have some generic Grignard reagent. The carbon is going to be way more electronegative than that magnesium. And then if we have CO2, this should be a carbon in the center. It's generally not thought of to be a good electrophile, but a Grignard reagent like this R is so good as a nucleophile, it can attack into the CO2. So we're going to show this Grignard attacking the CO2 and kicking electrons over. Actually, let's keep the coloring the same. And then in our last step, all we need to do is to treat this with an acid, and we can get to our neutral carboxylic acid. I did really briefly want to talk about specific naming conventions. This is quite obviously a carboxylic acid. This is called a carboxylate. A carboxylate has that negative charge, so you have to change the suffix to the ate suffix. Carboxylic acid implies that we're talking about something neutral. All right, so that's where we're going to stop for right now. When we come back, we're going to look at reactions of carboxylic acid.